The spaghetti bridge design chosen was a box truss design with cross bracing throughout the whole structure. Cross bracing is used in construction as a way to reinforce a structure with intersecting diagonal supports. It is especially used to increase a bridge structure's ability to withstand wind and seismic activity, because within the structure, the columns and beams carry vertical loads, whereas the cross bracing system is responsible for carrying lateral loads. Cross bracing only needs to carry tension forces, which will be effective for a spaghetti bridge, as spaghetti is quite weak in compression but can be much stronger in tension. The use of space gas analysis software allowed the design of the bridge, including dimensions, to be drawn up as a 3D wireframe model. For the construction of the spaghetti bridge, multiple strands of spaghetti were glued together using the Celli superglue to form what would become a member of the bridge construction. Once the spaghetti was cut to the correct length, these members were made to be 3 or 4 pieces of spaghetti thick, and the superglue bonded them together, acting as the bolts of the bridge to form its joints. Due to the box truss design, the square panels of the bridge were built separately, and then cross bracing added on both sides. These square panels were then glued together side to side to form the long sides of the bridge. More spaghetti members were used as a connection between the panels to provide a strong connection, and so the side of the bridge acted as a single structure. With the two sides of the bridge built, members were used on the top and bottom to create the bridge's width. During this test, the spaghetti bridge was able to withstand the loading from the testing apparatus until it reached a structural failure point of 2 kg or 19.6 newtons. This failure occurred at the supports of the bridge, as there was not sufficient support strength at either end, placing a significant amount of the loading on weaker members that quickly failed. The weight of the bridge was only 49 grams, which was well below the maximum of 200 grams, so a lot more material could have been used to improve the bridge's structural strength, therefore greatly enhancing its load capacity. The purpose of this initial test was to act as a starting point from which the cross-braced bridge design would be analysed and improvements could be made, so a much more effective bridge design could be constructed for the final test. By using the failure load of 19.6 newtons from this test, a structure analysis was done on space gas analysis software, which is capable of analysing the structure and can determine which members of the bridge were in tension and which were in compression when it was subjected to the loading test. The image shows the members of the bridge which were under compression during the test highlighted in orange. Spaghetti is a brittle material that can be reasonably strong when in tension but very weak in compression. So, to improve the loading capacity of the bridge, the compression members must be made as short as possible to reduce the possibility of buckling. By identifying those members which are under compression with space gas, a new bridge design could be developed with these members being significantly shorter and therefore stronger. This new design for the final bridge that was to be presented was also drawn up on space gas software. This spaghetti bridge was able to hold its structural integrity in this test until it reached a failure point of 6 kg or 58.8 newtons. This improvement from the initial test was partly due to the more effectively reinforced supports at either end of the bridge, giving it a better footing on the testing machine. The point of failure of this bridge was located at the middle panel where the force was being applied. This failure was due to one of the compression members along the top of the bridge buckling and failing, and soon after, one of the bottom members came away from its connections. This test provided a failure which was much more accurate to what was expected than the failure of the initial test, as the supports were stronger and the bridge was able to carry a larger force. From the test results, the load-weight ratio can be calculated to give a single number to represent the true strength of the bridge structure. This is done by dividing the failure load of the bridge by its self-weight. Therefore, load-weight ratio equals 6,000 grams divided by 99 grams. This calculation gives the spaghetti bridge a load-weight ratio of 6.6. During the construction phase, more care could have been taken to ensure more accurate measurements of each member, as some members were not the same length, and this meant the bridge was not fully symmetrical during testing. This was especially apparent at the cross bracing, where members were not connected in the same position on the panels due to differing lengths. Also, the points at which multiple spaghetti members were connected should have been more carefully and logically designed so a sturdy connection was achieved. Unlike the Space Gas software, which was only a wireframe model, the Spaghetti members have thickness, so these connection points weren't executed as effectively as in the design phase. Overall, the construction of the Spaghetti Bridge was rushed due to poor time management, and this meant loss of quality in the final structure. With more time spent on developing a sound strategy of how to connect multiple members at a point, the bridge could have been more aesthetically appealing. The members themselves could have been made much thicker as well, greatly increasing their strength, because both bridges were well below the weight allowance of 200 grams. Although spaghetti is characteristically a very weak material, it can offer a good insight into the importance of design and engineering processes. When these processes are used effectively, a material that is not seen as an obvious construction material can appear quite strong when subjected to loading. By using knowledge of trusses, tension and compression forces, and the characteristics of spaghetti, the group was able to construct a bridge made solely of spaghetti and superglue that was capable of carrying a substantial amount of weight. Better time management would have allowed the bridge to be completed at an even higher standard, giving it the ability to withstand higher loading forces, and emphasizing even further the ability for a weak material to be used to construct a strong structure when design and engineering processes are used effectively.